Alright, let's do some example problems on buoyancy. Our first problem. We make a very thin spherical shell of plastic and fill the inside with helium at atmospheric pressure. If the outer radius of the sphere is 1 meter, the density of the helium gas is that, and the density of the surrounding air is this, and the density of the plastic is the other. How thin must the shell be for the sphere to float in air? So what we have here, we have a sphere, alright, it's filled with helium, and what we want to happen is we want the buoyant force to exactly cancel gravity. Okay, so we're told the outer radius of the sphere, and I'm going to call that r. Let's call the inner radius a. Alright, we'll use that in our calculations, and then if I find a, then the thickness of the plastic is just the outer radius minus the inner radius, right? And we are given, in addition to the outer radius, we're given the density of air, we're given the density of helium, and we're given the density of the plastic. Okay, so how are we going to work this problem? Well, what we want to do is we want the buoyant force to just cancel gravity. So we want the buoyant force to be equal to gravity. What is the force due to gravity? So the force due to gravity is just going to be the mass of the helium. The mass of the helium is the density of helium times the volume of the helium. Alright, so the density of helium times the volume will give us the mass, and then we multiply by g to get the force. What's the volume of the helium? It's just the volume of a sphere, 4/3 pi, and the helium has a radius equal to the inner radius, right? The helium's on the inside. Then we have to add in, multiply by gravity, that gives us the force of gravity on the helium, but we also have the plastic. What's the force of gravity on the plastic? Well, it's the density of the plastic times the volume of the plastic, which is, well, let's see. If it were a solid plastic sphere, it would be 4/3 pi r cubed, but it's not solid, right? It's got the inner radius is carved out of it. A sphere of the inner radius is carved out of it, so I just take this minus the volume of the inner sphere, right, of the volume of the helium, and that just gives us this equation right here, right? So 4/3 pi outer radius squared minus 4/3 pi inner radius cubed, and when I subtract the two I can pull out the 4/3 pi and I'm left with that. Then we multiply by gravity. So there's the force due to gravity acting on the helium and the plastic together, so on our entire object. What's the buoyant force on our object? Well, the buoyant force is just the weight of the displaced fluid, in this case air. So it's going to be the density of air times 4/3 pi outer radius cubed, right? So now all we have to do is we set these two equal to each other. So the buoyant force is equal to the force due to gravity. Rho plastic 4/3 pi r cubed minus a cubed g. Okay, so when we write it like this, if the buoyant force over here is equal to the force due to gravity, it'll float. If the buoyant force is greater, it will accelerate upwards. If it's less, it'll sink downwards. This is just what we need for it to just float in the air. Alright, so notice we can cancel out the 4/3, we can cancel out the pi's. I left off a g here, right? The weight of the displaced air, also it's the density times the volume gives us the mass, and then we have to multiply by gravity. So I left off the gravity there, put it back in. I noticed that because I knew I should be able to cancel out gravity. There we go, and then we're just left with the density of air times the outer radius cubed is equal to the density of helium times the inner radius cubed plus the density of plastic times the difference between the outer radius cubed and the inner radius cubed. Alright? So this equation we ought to be able to solve. We can solve for a cubed, right? Then take the cubed root, and that'll give us a. Once we have a, we know the thickness of our plastic is just the outer radius minus the inner radius. So you should be able to hopefully work this all out and plug in your numbers and get the right answer at this point. So I'm not going to work it any further. I'm going to make a quick point here though. Chances are the thickness is going to be pretty thin. Alright, the density of the plastic is way higher than the density of the surrounding air. So probably it's going to have to be a pretty thin plastic shell. So you might think maybe I can get enough digits of precision by making an approximation. Alright, so you know, maybe you can, maybe you can't, but in particular if you're an experimentalist trying to figure out whether something will work, oftentimes approximations are great. You can do your calculations quicker decide if something's even feasible, and then go back and do a more careful calculation. So let me show you how you could get your answer quicker, making an approximation by approximating that the shell is so thin that I can do some cheats. All right. So when we calculate the force due to gravity, what I'm going to do is I'm going to say, well, first of all, let's look at the weight of the plastic. The weight of the plastic, we had to calculate the volume of the outer sphere minus the volume of the inner sphere, right? But if the shell is really, really thin, we might say, oh, I could probably calculate the volume of the shell more simply just by taking the surface area of the shell, 4 pi outer radius squared, and then multiply by the thickness of the shell, right? Now that's not true if the thickness is big, but for a really thin shell, right, it's almost like, you know, the outer radius and the inner radius are so close together, I can get away with doing that. All right, and then to calculate then I multiply by g, right? Then to calculate the weight of the helium, I take the density of helium times the volume of the helium, pi. But instead of using the inner diameter, since the inner and outer diameter are so close together, I'm going to say, well, it's approximately that. All right? And then when I do my equation, right, the buoyant force is just the weight of the displaced air, density air, 4/3 pi r cubed. When I set those equal to each other, I don't have a anymore. I'm solving directly for t, so I don't have to do any cubed roots or anything like that. It just makes the problem a little bit simpler. But remember, this is an approximation. The value you get for t isn't actually correct, but it hopefully will be really close. In the limit, as the thickness of the shell is infinitely thin, it will give us the right answer. Anyway, just thought I'd tell you a little bit about making an approximation. All right, our next problem. A block with a length of 10 centimeters, a width of 8 centimeters, and a height of 6 centimeters sits on the bottom of the lake at a depth of 15 meters. What force does a diver have to exert to pick up the block? Okay, first of all, this problem has an error. I just realized you need to know the density of whatever the block's made out of, or else you can't answer this. So let's assume that our problem also gave us that. So our givens are the width, the length, the height of the block, the density of the material the block is made of. We, can look up the density of water, right? So even though it's not stated in the problem, it's a constant. It's essentially a given, right? We're told it's water. And we're told the depth of the block, all right? So in order for the diver to pick up the block, if the diver's holding the block and not accelerating, the block's not accelerating, that means that the sum of the forces are equal, all right? And if the diver's picking it up, there's no normal force on the bottom anymore. The diver's providing that force, all right? So if the diver's holding the block up in the water, that means there's no net force on it. So what that means is when we add the force of gravity on the block, plus the buoyant force on the block, plus the force that the diver exerts, all right, we'll call that D on the block, those should all add up to 0. Well, what's the force due to gravity? The force due to gravity is downward, so it's going to be negative mass of the block times G, all right? The buoyant force is going to be, let's just call it the buoyant force for now, plus the force of the diver, and that has to equal 0. So that means that the force that the diver has to exert is going to be, if we bring this to the other side, the mass of the object times gravity minus the buoyant force. And this, we can read this. This is like a sentence. It's telling us the diver has to exert whatever gravity is doing on the block minus whatever the buoyant force is doing, right? So gravity's pulling down on the block, buoyant force is doing its part to hold it up, but it's not doing enough. The diver just has to give the rest, all right? So what is the mass of our block? Well, it's just the density of the block times the length times the width times the height times G. So there's the force due to gravity. Then we subtract the buoyant force. What is the buoyant force? It's just the density of water times the volume of the block times G, right? It's just the weight of the displaced water. So now I have an equation to find the force the diver has to exert, and I just have to plug in these known things, and I get my answer. So there you have it.